All right, welcome to Next Gen Manufacturing. Today, we're going to talk about something that quietly, secretly bleeds profit from just about every single machine shop out there: toolware. I mean, think about it. It's like this hidden tax on every part you make. It's the silent killer of productivity. And today, we are going to break down how to spot it, diagnose it, and most importantly, how to beat it.
I mean, it sounds kind of crazy, right? You've got this multi-million-dollar machine, an absolute beast of power and precision, and the whole thing just stops dead. Why? Because one tiny, worn-out tool gave up the ghost. And look, this isn't just annoying. This is downtime. This is when your profits just evaporate into thin air. It's good parts suddenly becoming scrap. It's literally money just bleeding out second by second. So, let's get right into it. Before we can even think about fixing this, we've got to understand exactly what we're dealing with. Look, every single cutting tool is going to wear out. That's a fact. But the real key, the secret sauce, is controlling how it wears and when it fails. That control, well, that's the razor-thin line between making a profit and taking a loss.
So, what even is toolware when you get right down to it? Well, at its core, it's just the slow breakdown of a cutting tool from doing its job. You can think of it like erosion, but on a microscopic level. It's caused by the absolutely massive heat and pressure of forcing a tool through metal.
And this slide right here, man, this lays out the stakes perfectly. On one hand, you've got your optimal, healthy tool. It's making clean cuts, beautiful parts, and, money. But on the other side, a worn tool. Now you're getting a lousy surface finish, your dimensions are all over the place, and that really valuable piece of material you started with, it's on its way to the scrap bin.
All right, let's start our diagnostic. And we're going to begin with the number one most common culprit you're going to see: abrasive wear. This is that slow, steady grind, the one that just dulls down even the toughest tools you've got. So, what's the telltale sign? What are you looking for? It's something called a wearland. You'll see it as a little flat spot, a uniformly worn down area, right there on the cutting edge. And as that little spot gets bigger and bigger, your tool gets duller, it's not cutting as well, and worse, it can actually start changing the size of your part. All of a sudden, you're out of tolerance. Okay, so what's actually causing this? It's mostly just straight up mechanical abrasion. Imagine tiny, super hard particles inside the material you're cutting. They act just like sandpaper on that cutting edge. And this gets way, way worse when you crank up the speed, because that generates heat, and heat softens the tool, which just makes it even easier for that grinding to happen. Now, this is where it gets interesting. This is how we start fighting back. Just look at this chart. Yeah, bare carbide is tough, absolutely, no one's arguing that. But look at the micro-hardness of a tin coating. You see that jump? We're going from around 1700 HV all the way up to over 2200. That's a huge leap. That coating is basically a suit of armor for your cutting tool. So the main thing here is you gotta be proactive. You can't just wait for it to fail. Your game plan is simple. First, use those advanced tool coatings to give it that armor. Second, get your coolant dialed in to pull that heat away. And third, start thinking about a smarter tool path, which, by the way, is a super powerful idea we're gonna get to in just a bit. All right, on to the next case file: chipping. Now this is a whole different beast. Unlike that slow grind of abrasive wear, chipping is sudden. It's a mechanical break on the cutting edge. It's that tiny little nick that, boom, causes huge problems in an instant. You're gonna spot this in one of two ways. You might get lucky and see the actual physical nick on the tool itself when you're inspecting it, but honestly, more often than not, the first sign is going to be a bad surface finish on your part. That chipped, uneven edge leaves these ugly lines and grooves and just ruins the quality of the workpiece. So, who are the usual suspects here? It almost always comes down to too much force all at once. Think about shock loading, where the tool just smacks right into the material instead of easing in. Or intense vibration, that horrible chatter sound during a cut. And interrupted cuts, oh man, those are absolutely brutal on a cutting edge and are a super common cause of chipping. Okay, so how do we stop this from happening? Your number one priority has to be stability. I'm talking a rock-solid, rigid setup with zero vibration. You gotta listen for that chatter, and if you hear it, you have to adjust your speeds and feeds right then and there to get rid of it. And if you know you're doing an interrupted cut, just back off the feed rate a little. Let the tool ease into the material gently. Okay, now we're at the most severe diagnosis, the absolute worst case scenario:
cracking and straight-up fracture. This isn't just wear and tear anymore. This is catastrophic failure, the kind that can wreck your machine, destroy your workpiece, and bring your whole production line to a grinding, screeching halt.
The first warning sign is thermal cracking. If you look really close, you'll see these tiny little cracks forming at a right angle to the cutting edge. What's causing them is insane temperature swings. The tool gets blazing hot in the cut, then cools down super fast when it exits. Hot, cold, hot, cold. You let those cracks go, and they're going to turn into chips, and eventually, the whole tool is just going to snap. Now, aside from that thermal shock causing the cracks, a full-on fracture often happens because, well, you're just pushing the tool way too hard. We're talking wrong speeds and feeds, trying to take way too deep a cut at once, or, and this is a big one, even something as simple as a loose tool holder. All of these create forces that the tool just wasn't designed to handle. So avoiding this is absolutely mission critical. Rule number 1, secure everything. Use good, high-quality tool holders. Make sure your workpiece is clamped down tight. Rule number 2, use the right parameters. A proper depth of cut is so important to stop the tool from deflecting and getting overloaded. Seriously, don't try to be a hero and take it all in one massive cut. Okay, so up until now, we've been looking at specific fixes for specific problems, right? A patch here, a tweak there. But what if there was a bigger strategy, a technique that could tackle the root causes of a lot of these wear types all at the same time? Well, there is. And this is where we get into the real next-gen defense, high-efficiency milling, or as you'll hear it called, HEM. And the core idea behind HMM is actually pretty simple, but it's a total game changer. Instead of hammering away with just the very tip of the tool, taking a really heavy cut, you use way more of the tool's cutting edge, but you take a much lighter cut. You're spreading the work out. You're spreading the heat out. You're spreading the load out. No single part of the tool gets beat up. And this right here shows you the difference perfectly. The old way, traditional milling, you take a wide but shallow cut. See how all that force and heat is just concentrated right on the tip of the tool? Now, HEM completely flips that script. You take a really light cut radially, but you go deep axially. You engage the entire length of the flutes. And this is exactly why HEM is such a game changer. It connects back to everything we just talked about. Because it spreads the load, it fights that abrasive wear. Because it keeps the tool constantly engaged in the material, it gets rid of the shock loading that causes chipping. And because it spreads the heat out all along the cutting edge, it's one of your best defenses against the thermal cracking that leads to fracture. It hits all of them. So what's the big takeaway here? It's this. Waiting for a tool to fail is, without a doubt, the most expensive strategy you can possibly have in your shop. But by understanding these signs of wear and taking action before it fails, using the right coating, adopting a modern toolpath like HEM, you end up saving tools, you save parts, and you stop throwing money in the scrap bin. So, I'll leave you with this to think about. Next time you're on the shop floor, are you still just reacting? Running around putting out fires every time a tool breaks? Or are you playing offense? Proactively managing wear with strategies that are built for the future? Because that choice, right there, is the difference between just making parts and building a true next-gen manufacturing operation.